I think it was. I think it was. I mean, he's a big DJ now, so.
I mean, I remember.
I think I think he's a DJ. He's playing with like
Oh,
Bush
where's
on
my
his
book?
Arab music.
He's one of the.
Where's half our class?
Yeah, exactly.
He's not like on their recording.
For sure. Yeah, so that's the craziest thing in the entire world. What is he thinking about? What's up, Elijah?
Current sells me a chocolate chip bagel and it's cinnamon raisin. Wait, what is that?
Good milk and Yaku is not milk, it's milk and salt.
All right, let's correct the homework. There were a lot of problems or questions. Some didn't take long.
What? No.
So we have page 390, 2, 3, and 4. Number 2, what do you guys get? Yep.
Oh, me. When the two pulses cross, the amplitude is 0.
Yep.
Because when they're rigidly attached, the reflected wave is off.
All right, and what kind of interference is this?
Completed destructive.
There we go. All right, that was easy. Number 3 then. Yep.
The new amplitude in that case would be 0.3,
Mm-hmm.
and it would be constructive interference.
All right. And then number 4, stretch string fixed at both ends is 2 meters long. What are 3 wavelengths that will produce standing waves on this string? And name at least one wavelength that would not produce a standing wave pattern. And explain your answer. Somebody else. Yep.
4 meters, 2 meters, and 1 meter.
Nope. 1 meter is in women. 1 meter.
Yeah, 'cause it's-
Which one would that be?
What?
Which 1 meter? Which harmonic would that be?
It's
Not
a
the third,
multiple
small-
of
the smallest,
half.
The 4th. Okay.
The fourth
Yeah.
one.
Okay. Yeah. This is the first, second, 1.3, 3, I think, is the third, this is the 4th. So this, okay. And then which one would it work then? Give me a number that wouldn't work.
12.
12. 12, 3. 3 is in between, it wouldn't work. 12 is way out here, wouldn't work.
Wait.
Something in between wouldn't work. Something here wouldn't work. If you said 0.8, you're not sure because you would have to see which one is the next one. But definitely 3 wouldn't work because it's right here in between. 12 is way out here. So, okay, and obviously there's an infinite number of answers for those that wouldn't work. And even those that would work because you could keep going to the 1,000 harmonic. Okay, so that was page 390. Now we have a bunch on page 394 and 395, which is basically review questions to see if you understand the chapter and stuff like that. Okay, we had number 1, what characterizes an object's motion as simple harmonic? Yes, Justin.
It describes periodic motion that's a result of restoring force proportional to the displacement.
Yep, there we go. That was a simple definition that I had written on board that one day. The key is you need all those 3 things happening. Many motions are periodic, but they're not simple harmonic. Because first of all, it's not even a back and forth motion. Like we go around the sun, it's not back and forth, so that doesn't work. And then some motions are periodic and are because of the restoring force, but still not considered simple harmonic motion because the restoring force is not proportional to displacement. And then, so then you need all 3 of those things to happen. Okay. And then we had number 3. Does the acceleration of a simple harmonic oscillator remain constant during its motion? Yes or no?
No.
No, of course not. Is the acceleration ever 0?
Yes.
Yes. And when or where?
Equilibrium.
At equilibrium. Okay. Now that question could have been asked a different way. It could have been asked, is centripetal acceleration ever constant? What would your answer be?
No, because the direction is constantly changes.
Centripetal acceleration is always towards the inside, so
Oh, you're right.
that does not change. So if the question was, is centripetal acceleration always constant? What's your answer? Because we know linear acceleration, which you don't have to say linear anymore, but that's not constant, we know about that. But what about centripetal acceleration? Is that constant?
Isn't it based on direction?
If you think of a pendulum, obviously you can't do centripetal acceleration for a mass consistent, there's no circular motion.
Sure.
But for a pendulum, that's going back and forth,
Yeah,
it's
Yeah.
yes?
I think so, because that's
What's the formula for AC again?
V over T.
Nope,
VF minus VI over T.
nope, say again?
Squared.
Oh, AC.
Yeah.
So, is AC constant?
No,
Why not?
because doesn't it depend on direction too?
AC
Well,
is
doesn't the
pointing
radius
inward.
Oh.
The radius change in the pendulum.
I don't know.
The string gets longer or smaller? Okay, so, is AC constant?
No,
Yeah.
no, the speed changes.
Speed changes. How would this be constant since you're going at 0 speed, maximum speed, 0 speed, maximum speed?
Yeah.
When is AC maximum?
At the
Top.
Equilibrium.
How do you get the tops?
What?
How do you get that AC is maximum at the top? At the extremity.
No, no mind. I got myself confused. I was thinking something else.
So when is AC maximum?
Equilibrium.
Why?
Because V is highest,
And when is AC 0?
when V is 0 at the top.
Okay. So you gotta be aware of those questions because of course I can ask you that.
But with a spring system, it's sort of about
Yeah,
the
of course.
opposite.
You can't even talk about this for spring because it's not in circular motion. Okay, so that was number 3. Now number 6. An ideal mass spring system vibrating with simple harmonic motion would oscillate indefinitely. Explain why.
Because the frictional forces are ignored in the ideal mass spring system.
There we go. So there's no friction, so M is conserved, so it's gonna keep going forever.
Oh.
All right. Then we had number 8. That's super easy. You're given Janet wants to find the spring constant of a given spring. So she hangs the spring vertically and attaches a 0.4 kilogram mass to the spring, so the end. Then obviously the spring is going to stretch because of the new mass. This mass has a weight, which the weight is going to be what?
4.
Oh, the
4 kilograms.
oh,
I mean,
the
4
weight is 4
newtons.
kilograms? I mean 4 newtons, I thought it was the mass.
What?
No, the mass
Oh yeah,
is
the weight's
point.
4, right.
And then the x that is stretched is 0.4, but it should be written as negative 0.4 in your formula because
Isn't it 3?
Yeah,
3 centimeters.
Oh yeah,
Well,
can
3
you read it?
centimeters.
So
0.03.
Yeah, 0.03.
So negative 0.03 meters, that means F
What?
elastic, which is negative kx, has to be equal to 4, which is has to be equal to Fg, which is 4, and you solve easily, you get that k is equal to what?
133.33.
newtons per meter.
2 decimals.
33.
33. Yeah. Newtons per meter.
There we go, that's an easy question. That would be typical multiple choice. So that's number 8. And then number 9, same kind of problem, just doing 230 divided by 0.4, so that gets you 580. 575, yes,
The
sir.
book said 5.
The book said,
It's
yeah.
just the rounding, because they do it
Yeah, I told
different.
you.
They do the rounding differently. Don't worry about that. So it's 575 newtons per meter. That's number 9. Number 10, a child swings on a playground. How many times does a child swing through the swing's equilibrium position during the course of a single period of motion? Yeah. Twice, that's correct, because no matter where you start from, whether you're going from here, you start from here to here, once, twice. If you start from here, you go this way, that way, and back. So you went 1 here, twice here, it doesn't matter. If you start from the middle, you gotta go here, here, and then back. So you still twice back. So it's twice through the equilibrium position, and basically in both directions. That was number 10. Number 11, what is the total distance traveled by an object moving back and forth in simple harmonic motion in a time interval equal to its period when its amplitude is equal to A. Support. 4A. So you can see it easily if you're doing spring mass system. Could be, let's say this is point A, this is point 0, this is point B, and then this distance, we can call this big A. So it goes this far, that far, back and forth. So it goes 1A, 2 A's, 3 A's, 4 A's, and that's one cycle. So 4A, 4 times the amplitude. And also if you do it with the sine curve, you start from here, you go all the way up to here for one cycle, so you went up A, then you went down A, then you went down A, then you went up A. So that's 4 A's, no matter how you look at it. Then we had number 12, how is period of a simple harmonic vibration related to its frequency? That's easy.
Reciprocal.
Reciprocal, that is not the proper word.
Oh,
Inversely related.
inverse.
1 over. It's inversely related. One goes up, the other one goes down. What's the next one? 13. What happens to the period of a simple pendulum? Listen up. I know this is easy, but still. What happens to the period of a simple pendulum when the pendulum's length is doubled? Yes.
The period would double.
Nope.
This is number 13.
Yep.
I got that it becomes root 2 times as long.
There you go. Because the formula says it's 2 pi square root of L over G, so the 2 is inside the square root, so square root of 2 times bigger. What happens when the suspended mass is doubled?
Nothing.
Nothing, because mass is not in the formula. We did it in the lab. Mass does not matter. And we had number 14, a pendulum bob is made with a ball filled with water. What would happen to the frequency of the vibration of this pendulum if a hole in the ball allowed water to slowly leak out? Yes, Marissa?
Nothing would happen to the frequency because mass doesn't affect it.
That's correct. Mass does not change anything because it's not in the formula, so it doesn't matter. Number 15, if a pendulum clock kept perfect time at the base of a mountain, will it also keep perfect time when it's moved to the top of a mountain? Somebody else. A lot of you guys have not spoken yet. I hope that doesn't mean you didn't do this homework. Some of you guys are looking very nervous right now. Emma.
I only went up to 12, I didn't write down.
Take a picture next time. Okay. Sure.
Acceleration due to gravity changes, so time changes.
That's correct. So be specific. So is it going to be slower, faster, whatever? Like what's going to happen to the period?
Faster.
So the period is going to go up or down? Should I say?
Down.
The period will go down because
Entire
I think it'll go up.
how'd you get? No, it's not going to go down. How would you get down?
I guess
I should do
Go
I
off.
don't know, I'm not sure.
I think if acceleration is less up there, it means it's moving slower. So if it's moving slower, it takes longer to do a period, so period would increase.
That's one way to look at it, but it's another way that's even simpler to look at it to answer that question. Why? You know for a fact that T
Oh,
will
well.
go up. Yeah.
Well, Fg is less up there, and if Fg is the restoring force, then if Fg decreases, then
Okay. There's also another way. That's even simpler to understand that T will go up. You go to the top of a mountain and you know for a fact that T is going to go up. How? That's another way. What's the formula for T?
T equals 2, oh that's pendulum.
Length goes up.
T equals 2 pi root m over 5.
Say it again?
T equals 2 pi root m. Oh, the pendulum? Oh, T equals 2 pi root L over AG.
Okay, so
Length goes up.
length goes up.
Ag changes.
How does length go up?
Ag changes.
Say it again?
Yeah.
Length decrease.
How does the length change when you go up to a mountain?
Oh no, Ag changes.
Gravity changes.
Okay, so how's that going to affect T?
As Ag goes down, T goes up. They're inversely related.
There we go. So at the bottom of a fraction, if AG goes down, T is going to go up, which means the pendulum is going to go slower. Number 16, right?
Yeah.
If your grandfather clock is running slow, how can you adjust the length of the pendulum to correct the
I
time?
was thinking.
First of all, when it says running slow, what does that mean? Is the period too long or too short?
Too long.
The period is too long, so that means you want to make the period smaller.
I was saying
So
that.
how can you change the length of the pendulum to make T go down? Yes.
Decrease the length.
If you decrease the length, T will go down. That is correct.
I was saying that for this one.
Number 17, a simple pendulum can be used as an altimeter, which is basically something that's going to measure the altitude on a plane. How will the period of a pendulum vary as the plane rises from the ground to its final cruising altitude. Yeah.
As the altitude increases, the period increases. Also,
And why is that?
because as it gets, isn't it the same thing as we just said? As acceleration due to gravity goes up, then
Mhm.
time would go up. So the period.
So acceleration goes up as you go up in the sky?
No, sorry. Acceleration goes down, so time goes up.
All right, okay. And that was the last one, right?
Yeah.
Okay. All right, so let's continue. So the test will be Tuesday. A lot of people have SAT stuff on Saturday. All right. So last time we talked about sound, talked about frequency, talked about pitch, talked about the speed of sound depending on the medium. We talked about tuning forks. Listen up. Compression, rarefaction. So your readings are to be section. Guys, listen up. Your readings are to be sections 1 and 2 of chapter 12, which is on sound, which we did section 1 pretty much last time. We're going to continue to the end of section 1, which is Doppler effect, which is not that complicated. Just want to make sure that we didn't skip anything. Talk about compressions, rarefactions.
The last note that we took was that the human hearing range.
Okay.
Oh, yeah.
Speed of sound depends on the medium. Sound can travel through solids, liquids, and gases. Oh yeah, we didn't talk about that much.
Yeah.
Okay. So, speed of sound, speed of all waves depends on the medium. We know that.
Can that be on Thursday?
No, that's impossible. Okay. So we talked about the fact that medium determines the speed of a wave. So for sound,
I'm ready to talk. I wrote test down. It's just-
guys, if you want to talk, you can leave. I will not mark you absent. You can walk out of the class right now. What?
The seniors aren't gonna be here Tuesday.
Is this day?
Yeah.
Yeah.
I guess you'll deal with it, but I can't put it Thursday. It's impossible. I have no way I can finish everything today. So that's not gonna work. So Friday, it was supposed to be Friday. A lot of people complained or asked if it could be changed to Tuesday because of SAT. I did that. I can't.
So he told him you should take it on Friday, take it on Friday? Is that possible?
Let me take out two versions of this test. That is not going to be convenient.
Okay, don't worry. It's fine.
We'll just
What
come
about,
in
can the
Tuesday
seniors
morning.
take it on Thursday?
We can come for
We'll just come.
No, but we have to be on.
What do you mean Thursday? Then the following Thursday?
On Tuesday.
Yeah.
We can take it the following. You can take it Wednesday, not Thursday.
Okay.
Oh.
So Wednesday morning.
When, okay, I have a free period, can I just come?
There you go.
Okay, perfect.
I have Hebrew, I'll come.
Okay. So the speed of sound depends on the speed of all waves depends on the medium. The speed of listen up. Listen up. The speed of sound, obviously, it's a wave. Depends on the medium. As the medium gets more dense, sound travels faster.
Faster, because like I'm the one. No, you didn't.
As the medium gets more dense, sound travels faster. Okay, so in order of speed, you would go from air. Then if you went to water, it would go faster. Then if you went to solids, it would travel even faster. Okay. And this is in general. There are some exceptions, but in general, as you get more and more dense, the sound will travel faster. Now, an exception is with air, for example. Hot air versus cold air. You would think that cold air being more dense, sound travels faster than cold air, but it doesn't. It travels faster in hot air.
Why would we think that it travels faster in cold air? It has to travel through less stuff in hot air because
Well-
it's less dense, it's thinner.
Yeah, but based on this definition, you should think that it would travel faster than cold air. Because
Medium's more dense.
cold air is more dense.
Yeah, for sure.
But sound of air, right here, sound of air is faster in hot air, and this is because the molecules have more energy.
So like
Basically,
sound is faster in like water.
yes. So the speed in air is about 340 meters per second. Water is about 1500 meters per second. The speeds don't matter, that I would give it to you anyway. Solid or solid like steel. So steel, for example, that's about 5,000.
That's crazy.
So
Now, in hot air, sound of air is faster because the molecules have more energy. Therefore, they're going to be moving around quicker and going to be bouncing off each other more often. And that's pretty much what's happening. The way sound travels, you could just pretend, let's say you had 4 people here aligned and you had a basketball. And you pass the basketball, and the time it gets to the last person, that's sound traveling. So if you have a lot of people in this room passing the basketball, that can, even though that's not really practical to think that way, but I guess depends on the way you think. But basically you can get the ball from one end to the other a little bit quicker that way. So it's like if you had dominoes all stacked up, the last domino is gonna fall sooner than if you had them spread apart. Right. So basically when they're more dense, everything's closer together, so it's easier for the sound to go from one end to the other. When it's less dense, it takes more time. But for hot air, even though it's less dense, the molecules are moving faster and have more energy, and therefore bump into each other more often, therefore sound travels faster. Okay. Sound waves travel in 3 dimensions, so when I speak right now, sound goes out like this, okay, in a sphere, not just, so that's why when you do this, it gets louder, because now less sound is lost this way, more goes that way, okay? So that's all that is.
So is it actually louder, or does it just sound like it's louder?
No, it actually is, because you have more sound waves reaching you instead of being lost that way and that way. And then the Doppler effect, which is the big thing in this section. Okay.
Yeah.
So the Doppler effect, you experience it pretty much anytime you hear a cop car or a fire engine truck with the sirens going off. You may not notice it, but basically the pitch goes up and then goes down. As the car's coming towards you with the sirens, the pitch goes up. As it goes away from you, the pitch goes down. And we're going to talk about why that is. So, the siren is emitting a sound, okay, at a certain frequency. Let's say frequency is, I don't know, 800 hertz. Just making up some number. Okay. The speed of sound in air is, let's say 340 meters per second. Okay. Now, as the car is moving towards you, okay, the medium has not changed. It's the sound is still traveling through air. So that means the speed of sound in air doesn't change. It doesn't matter if the car is going super fast or super slow. That doesn't matter, because again, the speed of a wave depends on the medium, not on what the person is doing. So the sound is being emitted at 800 hertz. That means 800 cycles per second. Okay. So now so let's say this is the car, truck, that's traveling to the right. And let's say you are right here. Okay. So this sound is coming out, coming towards you. Now, these sound waves right here are going to reach you more often when the car is moving towards you. Because and I had this demo, but I don't have anything to throw. But last year I used some kind of paper stuff that I found this class, I couldn't find them today. So I'm going to just talk about it. Basically, what I had somebody sitting on the chair, and I had let's say these paper balls, and I was just throwing them to the student. And at first I wasn't moving, so I threw 1 per second, 1, 2, 3, 4. The person was catching it, 1, 2, 3, 4. And then I started moving towards the student and do the same thing at the same frequency, 1 per second. I didn't increase my frequency, I didn't change the speed or whatever. But I was moving towards the student. Therefore, the student was catching them more often. Because every time I threw one, by the time I threw the next one, I was already closer. Therefore, it took less time to reach them. And then I threw the next one, I was closer. So that person was doing this, and all of a sudden they were coming in at a higher frequency, even though my frequency was the same. Okay. So that means the receiver here is going to receive the sound here at a higher frequency than 800. Okay. So maybe it's 850. I don't know what these numbers are, I'm making it up. But basically, this person receives this sound at a higher frequency, and therefore you hear it at a higher pitch.
But the frequency of the siren is always 800.
Yes, it has not changed. This is the frequency, guys. This is the frequency received by the receiver. The frequency emitted by the emitter has not changed. That is very important. Okay. I understand seniors, I know you guys are almost done, which I understand is tough to stay focused, but at least let other people who are not done focus. Okay? So anyway, the person receiving the sound waves receives them at a higher frequency, even though the emitted sound waves were still 800. That did not change. So if you can visualize the person catching the balls or whatever I was throwing at them more and more often because I was approaching them, that's what's happening. And then we did the same situation where this time I'm the emitter, I'm not moving, but the person who was receiving them moved towards me. Same situation. The person who was catching them was still catching them more and more often because every time he caught one, by the time he had to catch another one, he was closer. Therefore, it took less time to get to him. So the Doppler effect, it doesn't matter if it's the emitter or the receiver, or if they're both moving towards each other, okay, you will get higher frequency. So the Doppler effect, the definition is, let me give you the proper definition.
Is that because the air is denser?
No,
Not at all.
I didn't talk about air at all here.
Yeah, I know, but like as it gets closer, like why does frequency increase as it gets closer versus? Oh, because more waves are hitting you at the same time. Yeah.
Okay, here we go. So the Doppler effect occurs whenever there is relative motion between the source of waves and an observer. If the observer is moving instead of the source, so let me give you this definition, it's better. Doppler effect, there you go. Doppler effect is an observed change in frequency when there is a relative motion between the source of a wave and an observer. So I'll repeat that again. The Doppler effect is an observed change in frequency when there is relative motion between the source of waves and an observer. And it's on page 409, if you're looking for the definition, top right, 409. Doppler effect, an observed change in frequency when there is relative motion between the source of waves and an observer. So, relative motion, what does that mean? That means that you're either getting closer or you're getting further apart. That's what that means. So we just talked about the situation when you're getting closer. So the truck is approaching the person, or it could be the person approaching the truck. It doesn't matter, okay, it's relative. Or obviously it could be both of them going towards each other, which is even more, okay? So this is, what's important here is that this is while they're approaching each other. Okay, this does not mean, oh, if I get close to the truck and then stop, Doppler effect. It's like, no. Doppler effect is going to happen while you're getting closer. Or while the truck is getting closer, while you're getting closer, it doesn't matter who, but while this is happening. As long as the two are getting closer, whether it's because this one is getting closer or that one or both, Doppler effect. The observer will receive the waves at a higher frequency. If it's sound, that means higher pitch. If it's light, that means higher frequency. If it's radio waves, higher frequency. Okay, it doesn't matter which kind of waves you're talking about. Doppler effect works with all waves. Sound is the one you can experience all the time, but it works with all waves, yes.
So since the pitching, what happens to like actually how loud it is? Because obviously it's louder when like you're standing right next to it.
That's just, yeah, the loudness, that's because you're closer. That's all it is.
But
I mean,
is there like a reason, like what, does something happen with the waves?
well, because loud, again, this is the situation right here. When you speak, sound travels like this. It's like in a sphere.
Right.
So basically, if you're here,
Oh,
you only got what? This portion of it.
yeah.
If you're here, you get a lot more. That's all it is. Okay, so as I speak, this sound is just going out like this. So less of it is reaching you than if you're close to me.
So, and that makes sense then if you go like this, why?
Yeah.
Okay.
So the Doppler effect has nothing to do with that because that's just because you're close.
Okay.
This is about I'm getting closer, therefore I'm receiving the waves more often. Okay? And there's a formula that you would learn in AP, which is not for this class, that would tell you, based on the relative speeds, what will be the change in frequency. Because if you're getting closer at a more rapid pace, the change is going to be greater. Okay? But that's not important. Just know that if you're getting closer, this frequency is higher than what's actually emitted. That's what you need to know. And then obviously the opposite if you're getting further away. So when the truck goes away from you, okay, so now you hear low frequency. So that's why you hear the frequency go, it goes down. The frequency, the sound did not really do that. The sound was constant, okay? But for you, the observer, you hear high frequency because it's coming closer to you, then the truck passes you, it's going further away from you. Now the frequency is lower than what's emitted. So 780, whatever, 720, I don't know what these numbers are, I just know it's lower. So when the receiver and the observer are getting away from each other, this is when you would hear a lower frequency. Okay, does that make sense? Okay, and again, picture somebody, I'm throwing something to him, and now I'm backing away as I'm throwing them. Obviously, he has more and more time to catch them. Every time I throw one, next time I throw another one, I'm further away. It takes more time to get to him, so he has more and more time. He's like, this is easy. I'm going towards him, he's like, whoa, this is too fast. Slow down, like I didn't do anything. I did not change the frequency emitted. It's the frequency received here, okay? So that's very important. So if you are in the police car or on the fire truck, you hear the same sound because there's no relative motion between you and the emitter. You're going along with the sound. You don't experience the Doppler effect because you are with the sound at all times. So there's no relative motion. The key here is relative motion. Getting closer, getting further away. If you're both moving at the same speed, there's no relative motion. There's no Doppler effect. So let's say there are two cop cars that are just racing each other, going somewhere. There's no Doppler effect if they go at the same speed.
They'll both hear the 800 hertz.
Exactly. Okay. So let's see. Okay, next one is sound intensity, which is on page 410, which is section 2. That's just a simple formula, we're going to do some problems. So sound intensity, the intensity of a sound. So we're going to talk about intensity of sound, we're going to talk about decibels, stuff like that. See how all these things relate to us. Okay, so sound, like we said, when sound is produced, it basically travels in spheres, okay? Travels outward like that. So the intensity of a sound, the intensity of a spherical wave.
That's how loud it is. Right?
I mean, loudness, we're going to get to that in a second, but loudness is like a different perception of intensity, decibels, all those things are kind of like related, but it's not exactly how loud it is.
So what is intensity? Like how can I think?
It is loudness, but it's not as simple as that. So I'll try to find a way to explain it. That's not an easy concept to explain because loudness has its own thing because humans perceive loudness differently. Like you can double the intensity and the feeling of how loud it is not doubled. It's just weird. So I'll get to that. Intensity is equal to, this would be like what a machine would pick up. That's why loudness is like what humans pick up. That's why it's not exactly simple. So intensity, that's just P stands for power over 4 pi times r squared. This is the area of a sphere, right here. So if you had a sphere of radius r, that would be the surface area, 4 pi r squared. That's how sound travels in a sphere. Okay. So it's the power divided by that sphere, that's the intensity. Okay. And then power is in watts, if you remember from when we do the work stuff. The bottom here is going to be a meter squared. So intensity is going to be watts per meter squared. I don't think that unit changes. Nope, yeah. So let's do some simple formula, nothing crazy about this formula, but let's just do number 1, 2, 3, 4, 5, page 411.
Can I make it cooler in here?
What, 5. 5 equals. Wait, no, that's a power. What term? Okay. I get it.
Wait, what's the unit? Oh.
The power is.
If the distance is 5 meters, radius is half of that.
Wait, half?
Is our 5 meters?
Yeah.
Well, no, that
Radius. Radius is fine. Wait, radius is fine, right?
is it.
Yeah, it's fine.
Can we abbreviate intensity with I, or?
Nah, just write the whole word.
intensity?
I think for something else.
4, 5, 25, 100.
Yeah.
This is
25.
0.001. How would you round that? You can't really. I got 0.001. Wait, I did this 3.00.
So then, I'm gonna write this.
Right, 0.007.
Okay.
No, but it's a,
Yeah.
you gotta just remember, did you get 0.25 over 100 high?
0.5. The second one? Oh, no, I'm doing the second one.
The first one, did you get 0.01?
The first one I got 8
0.25.
over 4 pi times 5 squared.
Yep, 0.25 over 100 high. Should be a very small number.
Point. I just did this. 0.25 divided by 4 pi. I got 8. Look.
Yeah. And then this one is 0.
That's right.
Yeah.
To the power of negative 4.
Oh. Whoops.
Well, I'm just not bad.
I just kind of decided to ignore that. I don't know.
70, what is 70 in the power?
0.5.
Okay, so the 75
I did?
is.
Well, let me see. Yeah, this one I got
Oh yeah,
0.006.
0.002. Yeah,
You can write I, it's fine.
I, capital I,
This is.
right? Lowercase I made something.
We have 70 W.
Every letter.
One thing
1
we'll never
through
get is
5.
like amplitude. That is something.
And YT means amplitude.
I will never. Well,
Period.
period.
Period. 2.
I will never.
Oh. Is there another new program? What did you do? I accidentally put. My apologies. I assume you did it right.
0.001.
The intensity of Anderson's voice is like that. I walked from -4 and -7. W over meter squared. So that's
All these are in watts
this
per
is 2
meter.
meters per power to that person. We're trying to find the sound power source.
How is it?
So it's you didn't know. If you could go back and grab the phone. Don't, rubbing that on my bed doesn't make me feel better. Give me one.
For 5, you guys at 15.
We did a lot of
Yeah.
5, you guys at 15.
we overstocked. We stopped her.
We don't stop for it.
Just
I
need
did
the-
five it. That's it.
Intensity divided by the power.
I just did.
That doesn't mean the same thing.
Oh my god, how is it 7 meters to the power of 4 pi 25 squared? So that'd be,
Oh, yes.
Four.
I got 0, every 0.1, 0.01.
How?
Let me check it.
Yeah, power is just intended to be times 4 pi squared.
For the tuba, is that this distance? Intensity of. Oh, he's switching it up.
So Cora, what did you get?
I got 15.135.
That's, yeah, 16.
1.25 divided by that 1.2 number, then you divide that by 4 pi.
It's 4.2.
Then you divide that by-
So 229. 0.07. Oh my god.
4.82.
That's dumb. Because you're
Same.
the negative 3. So you clearly did something wrong. Why are you putting this?
What's your power?
Oh, yeah, you did it wrong. Reduce your you get 291 here. Yes.
Yeah,
you're-
okay.
And then 172. So you go.
I'll go do that.
And then, no, divide that by 4. If the answer is no, check it out. So first thing we do, can we all agree, the first thing we do is we take 0.35 and we divide it by 1.2 times 10 to the negative.
Let's just be like reasonable here and
Because
just
this is what it
acknowledge.
looks like and so
Let's just
this
acknowledge the fact that
is-
this is what we're bringing.
Cora, you answered.
You guys are done?
I know,
No,
so
no,
that's
no.
why they don't-
Yeah.
Not the whole thing is in disturbance.
Got 1.2 times 10 minus 3 times 4 pi.
And then you multiply by 4 pi.
You're wrong.
Oh, really?
Okay, now,
So this equals 0.015 r squared equals 0.35.
What? Really?
Narc,
Yes.
what's the answer for 5?
round
You get
I mean, we all got different things, so we're unsure what's the best way to do it. I think Emma's right, is it 4.817?
Yeah.
2
Zero
decimals.
point zero
4.82.
0.89 maybe.
Units.
So 0.00
Yeah.
Yeah.
yeah. 0.01.
Wait for five.
You best.
See, Shannon, you
Yeah.
were wrong.
Isn't five should be the one?
Wait, what was our answer?
Okay, so how did you do that? You,
What was our answer?
oh, you
Narc.
just wrote it down,
Narc.
it's just like.
For what? No, I'm correct, I'm sure I'm correct.
Anyway.
What'd you get?
I was looking for last night.
Square root.
I did square root it. It's the square root of 29 here. You want me to show you what I did in
Yep.
Wait, it's in the hard drive.
Yeah, guys, might have been more time.
It's so cool.
Is it 4.82 for 5?
Units.
Meters.
Just it.
Yeah, so if you multiply this times 4 pi, you get 0.05. And you just divide that over.
Get 4.52. You get 4.52.
No, it wasn't that, but it technically should work.
Oh,
So it was just like
4.82.
look at this.
If you divide by 4 pi, what I put in parentheses, it's gonna divide by 4 and multiply by 5.
Oh, really?
So go over here.
4.82
I didn't put 4
meters.
pi in parentheses.
That should work.
Narc 4.82 meters.
18.
No, it's not. It's kind
You
of.
probably just did a little.
0.6. 9.
I'm in radians, that's why. Oh.
Look, I'm really getting 4.52. I put like.
What is radians? What does that have to do with this? There's no degrees. This stuff.
No, she was in radians, that's why. She was getting her radians. Yeah.
No, but I'm saying like there's no degrees in this. There's no sine or cosine in here, so it shouldn't matter.
But then perspective though. I don't understand why it's not working then. It's not technically, the work is right, so I don't understand why. Tell me what I'm doing wrong, as I plug this into your calculator. Okay.
Oh, do you want us to bring it?
2 decimals, 96.
Then divide that.
And you get 2 more. All around, 37. 2 decimals.
Just, your calculator was making us fancier than everyone else.
Long units. Oh, sorry. This is correct.
No, but my can't do calculator.
Should we show it to them?
Look, okay, do the weird square root thing, do it.
On my calculator.
Like, in order to make this thing happen, do that with the calculator.
All right. What's the answer for 1A?
8 times 10 to the negative 4.
2 decimals.
7.96.
Oh.
10 to the negative 4.
Logs per meter squared.
B?
0.0016.
Nope.
0.002.
I mean, scientific notation. No, I could have been
2
wrong.
times 10 to the negative third.
2 decimals.
2.00. No, it's 10 to the
No.
negative third.
1.5 times 10.
2 decimals.
1.6.
Nope.
2.0 times 10 to the negative third.
Yeah, no.
We do 2 decimals all the time.
1.59
Thank you.
10 to the negative third.
Times what?
10 to the negative third. Watts per meter squared.
What's C?
0.01.
6 times 0 is
6.4 times 10 to the negative 3rd.
6.37.
2 decimals.
6.37.
6.37.
And 10 to the negative third watts per meter squared.
Number 2.
0.01 watts per meter squared.
Number 2, isn't it?
8.61.
0.
8.91, I think. So I got
8.9 to 10.
times 10 to the negative third watts per meter squared.
Oh, I got a syntax error.
No, that wasn't the
That's way different to
only if you do which sine and cosine.
Number 3.
2.31 times 10.
Watts per meter squared.
So again?
Watts.
Oh, I didn't know what we were doing, sorry.
Number 4.
4.82.
4.82 meters.
Okay.
Narc,
Yes.
for the future, if we were to get an answer, like, let's say it was 0.01, would you prefer that in scientific notation? Or can we just?
If it's just 0.01, that's fine, but if it's anything more where it has a bunch of decimals, just do it in scientific notation.
No, I have a question. So for intensity, is there like a type of motion that makes it more intense?
Oh,
Look at the formula. How would you make intensity go up?
More power. Yeah. No, but like a wave of like would what? I'm not getting this out right. Would a perpendicular motion have more intensity? Like perpendicular wave have more intensity than like a
More intensity, that just means speaking louder. That means more amplitude. That's what it means. Okay, listen up, listen up. Have a seat, Shannon. Okay, so last time we talked about the range, the human hearing range in terms of frequency, okay? But there's also a human hearing range in terms of intensity. Because obviously you know that if the sound is too low, if somebody's whispering too low, you're like, can you speak up? Because you can't hear, okay? So there's also intensity-wise where there is a range. Now there isn't an upper range where you don't hear it, but there is an upper range where you start to damage your ears. So there is a human hearing range. So if you have your book, page 412, look at the picture, because I'm not going to draw that picture. That's too complicated. Look at 412, the picture, top left, or the top of the page. That's a great picture right there. You should be familiar with. I'm not going to draw that because that's kind of complicated. But I will at least explain what that means. So look at the picture on page 412, and you see that you have the human hearing range with the frequencies at the bottom. So you see the frequencies go from 20 to 20,000 hertz. If you look at the left of 20,000 hertz, 20 hertz, you can't hear anything, okay, no matter what the sound is, intensity-wise. If you look at the right of 20,000 hertz, you can't hear anything, no matter what the intensity is. And then in between, you see, depending on the intensity, you can hear more or less. So if you look at a sound that has a frequency of 50 hertz, you see that you need to be relatively loud. Okay, you need it to be relatively intense to hear it at 50 hertz. If you are at a frequency of 500 hertz, you don't need to be that loud, that intense to hear it. So you can see that based on the frequency, okay, the intensity matters. Okay, so just be aware of that. You see the speech region, you see the music region, then you see threshold of pain. That basically when intensity is too much, you will physically damage your ears. So that's why when you go to concerts or whatever, and I know me as a DJ, I have to be careful with my ears. You can't be blasting music all the time because you will physically damage your ears, and that can't be reversed. When your ears get damaged, it goes down and down and down, and you can't change that. Yes.
Do you wear your earplugs?
I don't when I'm mixing because I need to hear the sound really well, but I do have my headphones sometimes when the music around me is too loud because that protects me. So I'll just have my headphones just for that because it's not good. But if I was gigging every single night, I probably would start doing it, wearing earplugs. Yeah.
so what's dangerous is when both intensity and power are big.
Well, no, because if you look at power, the intensity, it's dangerous no matter what the frequency is. So the threshold of pain is almost a straight line. So that means that the frequency doesn't really matter. If you get that level of intensity, you are going to be in pain.
So 10 to the 0, no matter what frequency you're
Pretty
at.
much. Okay. Yes.
Are things like a bass more intense than?
Yes, because a bass is going to be low frequency, but the thing is, bass moves a lot of air, so that's it to be more intense than a high pitched sound. But also high pitch, you can also damage your ears too. So you know, you gotta look at the frequency, but basically basses tend to be more damaging just because it tends to be louder. Okay. That's what it is. Question? No? Okay. So that picture, again, I'm not drawing it, but you need to understand this picture. Okay, that's part of your reading. So understand that the intensity matters. The next part that we're gonna do in the next 10 minutes is, guys, listen up, is decibels. Now decibels, that's how we perceive loudness, okay? The intensity, support, like you said, it is related to loudness, but it's not direct. It's not like, okay, this intensity is this, therefore it's this loud. We perceive loudness in a little different way, okay? And they say that we perceive loudness in a logarithm ratio, logarithm function. So it's not just some kind of linear function. It's like the log, okay? So if you look at the table, page 413, okay, the decibel table, page 413. Look at the decibel level and the intensity. So decibel level of 0 does not mean 0 sound. People think, oh, 0 decibels, that means 0 sound. That's false. That means we simply can't hear it. But there is still sound, because the intensity is not 0. So at the decibel level of 0, the intensity is 1.0 10 to the negative 12.
Almost 0.
It's very close to 0, but it's not. That's basically our threshold of hearing. Anything lower than that, guys, anything lower than that, you will not hear it. So that's why that's our 0 decibel level. Yes.
Can things like other animals and stuff hear?
Oh, I'm
lower
sure.
than that?
I'm sure.
But if intensity were really low, but then let's say you increase power like crazy, would you still be able to
What
hear
if you were
maybe?
wearing a hearing aid?
Intensity and power go together. If you use power, intensity goes up. That's the formula.
Okay, that makes sense.
And then you see now, if the intensity is multiplied by 10, you go from 10 to the negative 12 to 10 to the negative 11. So it's multiplied by 10, the decibel level goes up by 10. Okay. Now, if you multiply the intensity level by 10 again, decibel level goes up by 10. So you see how this works. Okay. If the intensity is multiplied by 10, the decibel level goes up by 10. So this means that, let's say you go from 20 decibels to 40 decibels. How much more intense did the sound get?
100 times.
100 times. Because every time you go up by 10 decibels, the sound got 10 times more intense. So that means 20 decibels doesn't seem like that much, but in reality, the sound got 100 times more intense. That's actually a big deal. Okay. If you go from 40 decibels and you say, okay, just pump up the music, and you go to 80 decibels, how much more intense did the sound get?
I have a question.
Yes.
I'm having trouble completely understanding how intensity applies to how intensity applies to sound. Like, is there any way for people to detect a change in intensity, or?
Yes, we perceive it, not like machines, but we perceive it. That's why this decibel is really how we perceive it. So when the intensity goes up by 10 times, so if the intensity is multiplied by 10, every time you multiply the intensity times 10, that's equivalent to plus 10 on the dB scale. When you're going to read this, it's going to make a lot more sense. So what I'm saying is that if the intensity is multiplied by 100, the decibel went up by 20. Okay. So if the decibel level goes from 40 to 80, it may not seem like a big deal. It's like, okay, it went up by 40 or whatever, but in reality, the intensity got multiplied by what?
1,000.
No.
100.
Not 1,000.
100.
Not 100.
Wait, 20 to 40?
10,000.
From where?
40 to 50, that's times 10. 50 to 60, that's times 10. 60 to 70, that's times 10. And then 70 to 80, that's times 10. So basically this whole thing times 10,000. 1, 2, 3, 4 zeros. That's how much more intense the sound got. That's a big difference. So now, think about if the volume, listen up, he's gonna start talking. If the volume has a decibel level of 0, okay, and you say, okay, pump it up, and then you bring the decibel level all the way up to 100 decibels. How much more intense did the sound get? From 0 to 100?
10 to the 10.
Say it again?
10 to the 10.
10 to the 10th. That's, you went from here, the sound got 10 to the 10 times more intense. Okay? So that's a big difference, of course. Yes.
Does intensity depend on a medium?
The intensity depends on the medium. Intensity is power. Oh, no. No.
So
That's a good
it could be like the same intensity in the water and in the air.
It doesn't depend on medium.
Okay.
Okay. So then, if you look at the chart, you see that they give you some decibels. If you whisper, 30 decibels. Mosquito buzzing, 40 decibels. Normal conversation, 50 decibels. Vacuum cleaner, 70. Lawn mower, 90. The horn of a car, 110. Threshold of pain, 120. So that's kind of weird how the car is real close to the threshold of pain. So to really, so that you can really hear it. And then if you go higher than that, you are basically above threshold of pain, like where you're physically damaging your ear. Thunderclap, machine guns, you don't want to be hearing those sounds a lot. And then a nearby jet plane, 150. So think about when you have your music, whatever, in your headphones, you got to be careful, because you might be damaging your ears without even knowing it. Okay. Okay. Next time we'll do.
I heard that there's like a car, a dragster, that its decibel level is like, and maybe even close to 300.
300?
Or maybe like between 200 and 300. I think.
What's a concert?
What is a concert? Let's see, is it on there? A concert? Well, it's not on there, but I would think that it's like 110.
110.
It's loud.
Yeah.
That's why you should wear earplugs. Yeah, that's enough for today. We're obviously going slower since we're adding another day before the test. So, okay, make sure you do your reading. There are no problems to do because this is more concepts than anything. Make sure you do your readings because this test, again, is going to be very heavy on concepts, not problems.
Feel better.
I just realized.